Yo, what's up, guys? Welcome back to another video. And today we're going to be talking about a topic that I've dreaded for so long, but obviously it's going to have to be taught at some point. Related rates. So essentially what related rates is the change of something at a specific point. So essentially what that means is, let's say you had a circle and you want to find the rate of change, let's say of the area. So you want to find the rate of change of the area. And then you're given either the radius and the change of the radius. And therefore you have to find the change of the area with that information. That's essentially what related rate says. Something is changing and you have to find that at that specific point how much it's changing by. What do I mean by this? Well, let's look at an example. And I think I'm going to separate this into two different videos because obviously there's so much problems out there containing related rates. But these are some of the ones I want to cover today. So let's say you had a rectangle. And let's say its width was 10 and its length was 5. And let's say you had the change of the width is -2 for some reason, I have no idea. And the change of the length is equal to, I don't know, 10. Why not? 10, why not? So now with these numbers, let's compute the change of the area. Well, first off, what most of these, no, all of these problems are all going to need some type of equation. The reason why we need an equation is because we can derive that equation, find the derivative of it, then just plug everything in. So from here, since we're given our variables, and since we need to find dA dt, or the change of the area with these variables, we have to come up with an equation. Obviously, the area of a rectangle is very, very easy to just derive because it's just area is equal to the width times the length. From here, what you have to do is you can't plug these numbers yet because you just have the general area. You have to do the derivative of this equation in order to find how much the area is changing at this point when these numbers are that specific. So we just take the derivative of it, so it's just dA dt. And remember, when we take the derivative, we have to take it with respect to time. So we have dA dt, which is equal to w dot dl dt plus L times dw dt. Essentially, what I just did was product rule because width and length are both variables. And so they're both variables, and since we're not constant, then you have to take the derivative of both of them. So essentially, we have the width times the change of the length plus the length times the change of the width. From here, you can just plug everything in. The width is 10, the change of the length is -2, plus the length, which is 5. I'm sorry, it's not 10. It's not -2. The change of the length is 10, plus 5, which is the length, times dw dt, which is -2. From here, you just have to simplify the letters. So 10 times 10 is 100, plus 5 times -2, which is -10, so it's just -10. And then dA dt is equal to 90. So obviously, there could be some variables like centimeters per second, or something like that. But in general, the change of area at that time with these variables is 90. I don't know what. That just means that the area is increasing by 90 at that point per second. And so let's do another one that's similar to it. Say you had a circle, like I said in the beginning. Say you had a circle, and This is the radius, right? You had the radius, and you want to find the change. You want to find the change of the circumference when the area is increasing by 100. I don't know, something like that, something like that. And so then let's say that the radius was 5 for some reason, I have no idea. So obviously we have the area, we're trying to find the circumference, not the circumference, the diameter. My God. So we're trying to find the diameter, how much is changing when the radius is equal to 5. So from here, what we can do is we can just set up our equation, which is area is equal to pi r squared. Now, this is the very, very important part. We know that the radius is equal to 5, but we're trying to find the diameter. What we can do is we can just set up a little equation that just says that the radius is equal to the diameter over 2. From here, what we can do is, since we're trying to find the change in diameter, you can just multiply by 2. So then we can see that 2r is equal to the diameter. Or really, you can just divide this as well by 2. Because since you're trying to find the radius, you're trying to find the relationship between the radius and the diameter, you can just keep it like this. So we just did some extra work. Hopefully it makes sense. So from here, we can just plug this in. Then from here, we get area is equal to pi d squared over 4. But we're not done yet. We have to find the diameter, but I think that's pretty easy because, again, you can just use your equation. Since the radius is equal to 5, it says 5 is equal to d over 2, and then 10 is equal to the diameter. So from here, we use our bridge equation. And since we know dA dt is equal to 100, we don't really have to find the area of it, we're just trying to find the change of the area, so let's just write this down somewhere. We know diameter is equal to 10. So from here, what we can do is, in order to find a change of diameter, we just take the derivative. So we have dA dt, or the change of area, which is equal to pi times 2 over 4 d dd dt. It makes sense. What we just did was we take the derivative of area, and then this is equal to pi times 2 over 4 of the diameter times the rate of change of the diameter. Essentially what I did was I just used power rule, -1, and that's how we got it. From here, we can just simplify everything so everything becomes easier. We have our variables right here. From here, what we can do is we can just plug in everything. We know the change of area is equal to 100, so it'll be 100, which is equal to pi times 1/2 times the diameter, which is 10, times the change of the diameter with respect to time. From here, we just simplify everything. 10 times 1/2 is 5, times pi is just 5/2 with the change of the diameter. And since we have to simplify everything, and since we're trying to find the change of the diameter, this is basically like saying 100 is equal to 5 pi x. This is our variable, and we're trying to isolate the change of diameter with respect to time in order to find the diameter, how much is changing with respect to time at this specific moment. So from here, we just divide by 5 pi. And then from here, we realize that the diameter, how it's changing with respect to time at this specific point, is equal to 20 over pi. And that's your answer. Now, this is going to be my final example. And I'm just making these up because like I don't plan these, like I don't know, I just like to make random examples. This is gonna be my final one. Let's say you had a sphere. Let's say you had a sphere. Let's say this is a snowball. That does not look like a snowball. The volume of a snowball, because it's a sphere, is 4 over 3 pi r3, right? And let's say you're trying to find the change of the volume when r is equal to 10 and dt is equal to 5. I've never seen a question like this before, and I promise you, I don't think you ever will. This is, oh my god. Okay, let's see. So we're trying to find the change of the volume with respect to time when the radius is equal to 10 and the change of the diameter is equal to 5. Since we're given radius, we know that the diameter is going to be 20 because the radius is equal to diameter divided by 2. From here, what we can do is, since we know the radius is equal to diameter over 2, what we can do is we can just simplify that and then just plug this variable in with respect to r. Now we have volume, which is equal to 4 over 3 pi times d to the third over 8, because 2 times 2 to the third is just 8. So now we can solve for this equation. We just take the derivative of this with respect to time. So we have dv dt, which is equal to 4 over 3 pi times 3d squared over 8. Since everything, times the rate of change of the diameter with respect to time. Since this is just being multiplied by everything, we just cancel out these three. So if we just simplify, we have the change of volume with respect to time, which is equal to 4 times pi times d squared over 8 times the change of diameter. From here, we can just plug everything in. So we have 4 times pi times diameter squared, and since it's 20, we just have 20 squared over 8 times the rate of change of the diameter, which is 5. So from here, we just simplify everything. 4 times 8 is just 1/2, so you could really just do 1/2 times pi times 20 squared, which is 400, oh my god, times 5. And then if you simplify everything, the rate of change of the volume at this specific time is equal, 400 times 5 is 2,000 pi over 2, or the rate of change of the volume is equal to 1,000 pi. I really hope that's right. But yeah, guys, this is just how related rates work. You're just trying to find the rate of change of something. You have an equation, you can memorize it. You have to memorize it sometimes. They just give you the equation sometimes, but it's better to just memorize them. But essentially, this is what related rates is. You're just trying to find the change of something at a specific point, and then you have a bridge equation that you have to plug everything in. And from there, you just take the derivative of everything in respect to time, because when you're trying to find related rates, you're trying to see how much they're changing at that specific time or that specific point. So this is part 1. It's very, very difficult, but I promise part 2 It's very, very more simple if you understand what you're doing. So this is related rates. Thank you for watching, and goodbye.